So in this video, we are going to discuss about coefficient quantization error. So usually this question is repeating in the university exam. So I am Vinod, assistant professor from the EC department. So first let us discuss about the quantization error types. There are 4 types of quantization error. One is input quantization error, coefficient quantization error, overflow error, and round off error. So what is input quantization error? This error is due to um, quantization of the input signal into a set of discrete level, such as the ones which is introduced by ADC. ADC means analog to digital converter. Next one is coefficient quantization error. This error is due to the representation of the coefficient by a finite number of bits. The coefficient AK and BK have a very high precision transfer function, but these coefficient must be quantized. Next one is overflow error. It is caused by addition of two large number of same sign, which produces a result that exceeds the permissible word length. So the last one is a round off error. It is caused when the result of the multiplication is rounded off to the nearest discrete value or permissible word length. So first let us discuss about coefficient quantization error. So in the design of the digital filter, the coefficients are evaluated with a infinite precision. When they are quantized, the frequency response of the actual filter deviates from which would have been obtained with the infinite word length representation, and the filter may actually fail to meet the desired specifications. So if the pole of the desired filters are close to the unit circle, then those of the filter with quantized coefficient may lie just outside the unit circle. So consider the second order IAR filter, infinite impulse recursive filter with h of z is equal to 1 divided by 1 minus 0.95 z power minus 1 plus 0.225 z power minus 2. So these two are the coefficient. One is minus 0.95 and 0.225. Find the effect of the quantization on pole location of the given system function in direct form and cascade form, and truncate the bits to 3 bits. Okay. So first let us discuss about the direct form one. So the given value is h of z is equal to 1 divided by 1 minus 0.95 z power minus 1 plus 0.225 z power minus 2. So first let us take minus 0.95. So 0.95 into convert into a binary number. Therefore, you have to multiply 0.95 with 2. So if you multiply 0.95 with 2, you will get 1.90. So after that, you remove the one, the left hand side value. Okay, so you will get 0.9. If you multiply 0.9 with 2, you will get 1.8. Okay, so after that, in the 1.8, you have to remove one value. Okay, so if you remove the one value, you will get 0.8. 0.8 into 2, you will get 1.6. Next, you have to remove the one value, you will get 0.6 into 2. So you will get 1.20. Next, you have to remove the 1, so you will get 0.2 into 2, you will get 0.4. So this step should be repeated. So here if you see 0.4 into 2, you will get 0.8. So again you will get 0.8. So this step is repeating. So I am going to stop this one. So if I get the final answer is like 0.000, you have to stop. Okay. So since it is for minus 0.95 base 10, the answer is from that point you can write 4 ones, right? 0.41001. Okay. So 0.41001. So you have to truncate it to a 3-bit value. That is, after point, you have to select only 3 bits. So if I select the 3 bits, I will get only 0.111. So what is 0.111? 0.111 is, if we convert 0.111 to this binary value, if we convert into a decimal value, you will get 0.875. Since it is minus 0.95, you have to write it as minus 0.875. So how to convert binary to decimal value? I will give it in the detailed in the description box. You can refer. And 0.1 represent 0.5, 0.01 represent 0.25, 0.001 represent 0.125. So if you add these three values, you will get 0.875. Okay. So next coefficient we see this 0.225. So since it is a decimal value, you have to multiply it by 2. If you multiply it by 2, you will get 0.450. Next 0.450, if you multiply by 2, you will get 0.9. 0.9 you multiply by 2, you will get 1.80. So you have to remove that 1. After that, 0.8 into 2, you will get 1.6. Next, you have to remove the 1. After that, 0.6 into 2, you will get 1.2. Next, 0.2 into 2, you will get 0.4. So you have to write it from 0.001110. So you have to truncate this value to 3 bits. So if you truncate it into 3 bits, I will get 0.001. What is 0.001? It is 0.125. So in the direct form 1 equation, that is h of z is equal to 1 divided by 1 minus 0. It is 0.95. So you have to replace it by minus 0.875. Similarly, 0.225, you have to replace it by 0.125 z power minus 2. So this is how you have to do it for the direct form 1. So next question is cascade form. So since h of z value is you can see the h of z value is 1 divided by 1 minus 0.95 z power minus 1 plus 0.225 z power minus 2. So if I change it into so if you see the cascade form, so if you multiply these two values, okay, so if you multiply 1 minus 0.5 into z power minus 1 into 1 minus 0.45 into z power minus 1, you will get the direct form 1. So the remainder I am going to split into two parts. Okay. So here I can see the coefficient value is minus 0.5. So 0.5 you have to multiply by 2, you will get 1.0. So 0.1 is your answer. 0.1 is your answer. So 0.1 I can represent it as 0.5, right? Next, minus 0.45. 0.45 you have to multiply it by 2, you will get 0.9. 0.9 if you multiply it by 2, you will get 1.8. 0.8 into 2, you will get 1.6. Next, 0.6 into 2, you will get 1.2. Next, 0.2 into 2, you will get 0.4. 0.4 into 2, you will get 0.8. So since the step is repeating, so you have to write it as 0.01110. So if you truncate it into 3 bit, you will get 0.011. Okay, so 0.011 is nothing but 0.375. Since it is a minus value, I am writing it as minus 0.375. So you have to write 0.5 minus 0.5 as it is, and you have to replace minus 0.45 value to minus 0.375. So this is how you have to do this problem. So I hope this video is useful for you. Thanks for watching.